So I figured we could do a little special relativity. It's not too difficult. This Einstein quote just basically says that no matter what, a light source coming near you is always going to be moving at the same speed. So if I'm on a train and I'm throwing baseballs at you, the baseballs are going to have the speed of the train plus whatever I threw it at you. But if there's a light on the front of the train, the speed of the light is always going to be the speed of light, no matter how fast the train travels. So that's kind of what we're going to go into, and how that affects time. So Einstein devised a light clock. And what the light clock is a 186,000 mile clock, so it's convenient, fits in your pocket. And it takes light 186,000 miles every second to, make one tick. 186,000 miles, light's gone 1 second, and it comes back. So our mirror is pretty much our talk. Tick, tock, and we have a light clock. So this is a picture of a stationary light clock. If we were standing still in a train, the train's not moving, we would see this. People on the outside would see this. But if we have an observer, we'll call Bob, who's standing on the ground, and he sees Alice go by in a train that's going a pretty high portion of the speed of light. He's going to see her light have to take this angled course. So from Alice's perspective, she's standing on the train, the light goes up, light comes down. But to Bob, Alice is moving across his reference frame, so as she moves across, the light has to go up and to the side to meet her mirror to send it back down on the other side. So that a person in one reference frame has a completely different view of how the light's traveling than someone in a different reference frame. So Bob would measure 2 ticks, but here at this up here, 0.995 C, that's 99.5% the speed of light. So at that speed of light, or at that speed, Alice's clock is ticking at about 1/10. So it takes her clock 10 seconds to travel up and 10 seconds to travel back in Bob's reference frame. So Bob's clock goes up, down, and then finally Alice's clock reaches the top. And then Bob would say that it took a total of 20 seconds in order for Alice to tick away 2 seconds on her light clock. So from Bob's perspective, Alice's clock is moving slower, so that from this we can see any person who is moving at a significant fraction of the speed of light is going to measure time moving more slowly. And that's where you get the twin paradox. If you have 2 twins that are on Earth and one of them leaves for a space trip for 50 years, moving at a percentage of the speed of light, and they come back, they will have aged, maybe a few days, whereas the other people would have aged 50 years. So from Bob's perspective, Alice's clock is moving a lot slower. And then in order to prove this, they took atomic clocks that can measure within an accuracy of about 1/1000th of a second, or a nanosecond, if you want the scientific term. So they took 4 atomic clocks, strapped them onto jets, flew the jets as fast as they could around the world, twice one way, twice the other way, just to prove, the motion isn't what's doing it, it's the actual speed. So when they brought them down, you're not moving at large fractions of the speed of light in a jet, not even close. You're moving pretty small, but if you're measuring billionths of a second, you're going to be off by several billionths of a second. So when they brought the clocks down and compared them with clocks that were on the ground, they found that the clocks had slowed by a large, or at least whatever was predicted by special relativity. The main application of special relativity has to do with GPS. If you want your GPS to be able to pick up where you are within a few meters, 5 to 10 meters especially, you have to have an accurate clock, not just clock on the satellite, but it has to be accurate with respect to clocks on the ground. So seeing as how most GPS satellites move at about 14,000 kilometers per hour, they're a little bit slower. So about every day, the average GPS satellite loses about 45 nanoseconds. But to get that 5 to 10 meter accuracy that you're looking for, you only need to lose about 20 to 30 nanoseconds. So after about 16 hours your GPS satellite's worthless, unless you know about special relativity. And I'm way short.
Ask questions.
Any questions? Yeah.
Oh yeah, I was going to say, as I like how that you covered the satellite thing, because like without it, like our cell phones wouldn't even work at all. But yeah, that's cool. I was wondering just if you think, because I love time travel, but you think time dilation indicates that there is such thing as excitement? It does, but I don't know.
Not in the reverse direction as much.
Not in reverse, but I mean,
like with speed, you wouldn't be able to travel through time. Like you would have to use wormholes, basically.
right, that's what they predicted, but assuming you could get the speed, because they technically are traveling through time in a sense.
Assuming you could go fast enough, the only thing you would do is slow down with respect to another observer. So I mean, you could, theoretically, if you could get your ship to go fast enough, you could go across the whole universe and have time left over. But everything else in the universe would be dead or decayed because you had been gone so long.
Right.
Everything in our galaxy, pretty much our sun, would probably be gone. It took you so long.
So is that minute amount, though, that it dilates? I was always like, would you consider that time travel? It is kind of time travel, a little bit.
It's to a degree time travel, but like especially if you were a scientist up there, every day you're going to get 45 more nanoseconds than we have. It's not going to extend your life by very much.